Hi. So, in the previous lecture, we spoke about several ways to deal with overfitting and speeding up the training, and now we're going to show some code to apply this. So, in this video, we're going to talk about this method here, which is weight initialization with Xavier. So in this notebook, we're gonna implement three ways of initializing the weights. We're gonna initialize first with zeros. Next, we're gonna initialize randomly. And finally, we're gonna initialize with the Xavier method, which is also referred to as he. So we start off by loading our dataset. So this is just a function to load our dataset. This notebook will be available in the link below. So let's say this is our, we visualize the dataset. Okay. Next, the model creation. So this is basically containing all the models that we need. So we, in the notebook called, or in the video called Lecture of Building Image Classification from Scratch, we actually have created all of these functions minus the predicts, minus the plotting the decision boundary. We just also had that at the bottom there. So again, we're not going to go through this because we have videos specifically describing this in details. So now let's take a look at our data, and this is how our data looks like. So if we initialize W with 0, what does it do? If we initialize it with just completely random values, what happens? And if we initialize it with Xavier, what happens? Does our model learn how to deal with this? We're gonna initialize a three-layered neural network in this example here. So we want to see how good will the neural network be able to learn from this. So let's start with the zero initialization, and we have here the doc string. So basically it takes in the size of each layer and it returns the values of W1, B1 up until WL, BL, containing all the zero initialization. So it basically initializes everything by zero, B and our weight and our bias. So let's take a look at that. So what do we have here? We can see that by the 14,000 iteration, the cost function doesn't go anywhere. And this is our iteration, and the cost doesn't change, which basically means the model has learned nothing. So when our weights are 0, initialized by 0, and our bias are initialized by 0, a neural network learns nothing. And this is how it looks when we plot it. Basically, it's a 50-50 because, yeah, why not? So basically, it has failed to classify any of these correctly. Now, random initialization. So we're just gonna initialize W and B by complete random values. And the problem with random initialization is that it leads to vanishing and exploding gradients, which means that either it slows down the optimization algorithm or it takes too long to actually get to the point by having large random values. Again, it simply takes in the size of each layer, and then you can see here it randomly initializes W and times it by 10. So it's like we're gonna have an exploding gradient issue here, and then it also initializes, and it initializes B with zeros. In the literature, initializing B, since it's a real number, by 1 or 0 or 2, it doesn't affect much, but W here is the one that controls the learning. So let's fire this up. We're gonna initialize it. Oh, and there we go. It's starting to learn. So as you can see here, the problem of the exploding gradient, eventually it kind of figures it out, but still, again, it doesn't go down as fast, but at least it's better than initializing weights by 0. So we see here we get an 83% on the train set and 86% on the test set. So if we plot that, we can see it's starting to learn. And I think if we increase this learning parameters to even more, eventually it will learn to get it right. So I was looking for this, so let's scroll down here. Boom, 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 boom. Okay, so what was it? 0 pointers. Let's just keep it here for reference, and let's see if we increase the iteration to 30,000 or even 50,000. Let's see if it actually eventually learns. Where did it go? 15,000. Let's increase this to 50,000. Let's see if this actually improves. And usually it eventually learns, but the whole point is to show you we want to speed up the training. So let's run this. It's getting better. Oh, and there we go. So it takes, you can see it's starting to flatten slowly. It's 0.04. So yeah, so as you can see here, increasing the number of iterations has reduced the cost function slightly. So by having an exploding gradient, learning is so slow. It takes so much more iterations to get to the point. So let's see with Saviar initialization, and the difference is we add this here. So we times it by the square root of 2 and divide it by the number of neurons in the L minus 1 layer. So in the previous, in the current neuron in this fact, because it starts at 0. So let's say here we multiplied it by 10, and earlier we had a 0 initialization. So if we execute this, boom, boom, oh, it's actually going to be up to 50,000 now. It might lead to NAND and 0. Actually, it doesn't. Oh, that's fine. But you see here the accuracy is 99.6% on the training set and 96 on the test set. This is fantastic. And here you see it's 0.014. Well, previously it was 0.3. 0.3. So you can see with Saviar initialization, actually, if it's not too big, if it's not too small, then this is the sweet spot. And if we plot it, we see, wow, a fantastic circle. So basically, in summary, with the 3-layer neural network with 0 initialization, we fail to break symmetry. That's why your training accuracy is 50%. Flipping a coin, basically, is it right, is it wrong? A 3-layer with a large random initialization with 2 large weights has 83%, and it takes much longer. And with a 3-rail neural network, you have an initialization with 99%. So this is a way to speed up your training process, is by using the Saviar initialization. Thank you all.